A civilian drone looks simple, for motors, a battery, a camera, and a remote control. But keeping that machine stable in wind, holding the horizon perfectly level, compressing high-resolution video, and transmitting it over kilometers requires a tightly coordinated technology stack. DJI did not dominate civilian drones by inventing every individual component. It won by making the entire stack behave like one product. Flight control, gimbal stabilization, imaging, radio transmission, propulsion, sensing, and mobile software were developed together, then manufactured at enormous scale. The result changed what buyers expected. A drone was no longer an experimental aircraft for hobbyists. It became a camera that happened to fly. To understand how a Chinese company created this position, we need to open the drone and examine each layer of the system. DJI was founded in 2006, emerging from a university dorm room project focused on flight control. At the time, building a multi-rotor was difficult. Hobbyists selected a frame, motors, electronic speed controllers, sensors, radios, and open flight software, then spent hours tuning the machine. The flight controller was the hidden barrier. It had to estimate orientation from noisy sensors and adjust motor speeds hundreds of times per second. DJI's early opportunity was not a glamorous camera. It was making unstable aircraft easier to control. By packaging sensors, control algorithms, and setup tools into a reliable product, the company reduced the knowledge required to fly. That foundation created a natural expansion path, from selling flight controllers to selling propulsion, gimbals, and eventually complete ready-to-fly camera drones. The flight controller is the drone's nervous system. Gyroscopes measure rotation. Accelerometers measure changes in motion. A barometer estimates altitude. Satellite navigation provides global position, while compasses and vision sensors add more references. None of these measurements is perfect. Motors vibrate, wind pushes the airframe, magnetic fields distort the compass, and satellite signals can reflect from buildings. The controller uses sensor fusion to estimate the aircraft's real state, compares it with the pilot's command, and calculates a correction for each motor. Good control software makes this loop feel invisible. The drone stops when the pilot releases the stick, holds position, and returns home when the link is lost. DJI's early strength in flight control became the platform on which every later feature depended. Stable flight is not enough if the footage shakes. A flying camera is constantly rotating, accelerating, and vibrating. DJI's next decisive capability was the motorized 3-axis gimbal. Tiny brushless motors and position sensors counter the movement of the aircraft, keeping the camera pointed in the desired direction. But stabilization is not only mechanical. The gimbal controller, camera timing, drone attitude, and image processing must cooperate with extremely low delay. DJI developed the ZenMuse gimbal line before integrating increasingly compact gimbals into consumer drones. At the same time, cameras improved from externally mounted action cameras to purpose-designed sensors, lenses, codecs, and color profiles. This integration transformed the value proposition. Customers were no longer buying an aircraft and then engineering a camera platform. They were buying a predictable aerial image. The next challenge was the invisible cable between the drone and the pilot. A control link must send commands reliably. A video link must compress the camera feed, transmit it through interference, recover missing information, and display it with low enough latency to fly. Early consumer systems often separated these functions and produced weak, inconsistent video. DJI integrated digital transmission into the product. Its OcuSync family, now represented by newer O4 systems, uses multiple antennas, adaptive frequency selection, encoding, and tight coordination between the aircraft and controller. Official DJI specifications show how the system can shift across different frequency bands under different regional rules. The headline range is less important than the engineering result, a clear, responsive image that lets an ordinary user frame a shot with confidence. A drone's propulsion system is also more than 4 motors. propeller shape, motor winding, magnets, electronic speed controllers, battery voltage, cooling, and flight software form one energy system. The electronic speed controller translates commands from the flight computer into precisely timed electrical power. DJI's own technical material describes controllers that monitor speed, voltage, current, and temperature, then report that information back to the main controller. Active braking and high-frequency control improve response and efficiency. When propulsion is designed together with the airframe, the company can balance noise, thrust, flight time, weight, and thermal limits. Competitors can buy good motors. The harder task is tuning every physical component and every control parameter so the drone feels calm, responsive, and predictable across thousands of production units. As drones became easier to fly, sensing expanded the safety envelope. Downward cameras and ranging sensors help hold position when satellite navigation is weak. Forward, rear, side, and upward vision systems detect obstacles. Some models use pairs of cameras to estimate depth, while mapping algorithms combine observations over time. The aircraft must decide whether to brake, reroute, follow a subject, or continue a programmed path. These features link computer vision with flight dynamics. A late or unstable decision is not just a software bug, it can become a crash. DJI gained an advantage by deploying algorithms across a large product family and learning how they behave in real landscapes, lighting, wind, and interference. Each generation turned more piloting skill into automatic behavior, expanding the market beyond experienced radio control enthusiasts. DJI's most visible innovation was product integration. The Phantom combined a stable aircraft, gimbal camera, navigation, remote controller, and mobile app into a recognizable ready-to-fly system. The Mavic line then compressed those capabilities into a folding body that could fit in a small bag. Many models reduced weight and regulatory friction for casual users. Enterprise platforms reused core technologies for mapping, inspection, agriculture, public safety, and automated docks. This product ladder mattered because research could be shared. Improvements in motors, image transmission, batteries, computer vision, and manufacturing moved across multiple price levels. Scale reduced component cost, while lower cost brought more customers and more real-world feedback. DJI was not selling one brilliant drone. It was building a reusable technology platform and continuously repackaging it for different users. Shenzhen provided another advantage. The surrounding Pearl River Delta contains dense networks of electronics suppliers, mold makers, machining companies, battery specialists, camera modules, circuit board assembly, and logistics. Proximity shortens the distance between an engineering decision and a physical prototype. A design team can change a board, enclosure, motor, or cable and receive new samples quickly. That speed is especially valuable in drones, where reducing a few grams can affect flight time, cooling, vibration, and image quality at once. DJI combined this manufacturing environment with substantial internal research and product testing. Competitors could purchase many of the same components, but they could not automatically reproduce the iteration loop. The real advantage was the ability to discover a problem, redesign the system, validate it, and scale the solution faster than the market moved. So how did DJI dominate civilian drones? It began with the hardest hidden problem, reliable flight control. It added a gimbal and camera, turning the aircraft into a creative tool. It integrated digital video transmission, propulsion, sensing, autonomy, batteries, controllers, and software. It used Shenzhen's manufacturing ecosystem to iterate quickly and scale globally. Most importantly, it removed complexity from the customer. Every layer reinforced the others, creating a system that was difficult to challenge with a single superior component. Regulation, security concerns, and geopolitical restrictions can reshape DJI's access to markets, and dominance is never permanent. But the industrial lesson remains. China did not win this category merely by producing drones cheaply. DJI won by converting a collection of difficult technologies into an appliance that almost anyone could unfold, launch, and trust.